a couple of other things about Mohr circles. You can have a three-dimensional system like you do in the real world, and then you have the Mohr circle for sigma 1 and 3, the Mohr circle for sigma 2 and 3, and this Mohr circle for sigma 1 and 2. And the three circles are going to overlap exactly like this, where this white one is the 1 and 2 circle, the small white one is the 2 and 3 circle, and the big kind of grayish blue one is the sigma 1 and 3 circle. If the sigma 2 and 3 are more similar, the two white circles will be more similar in size. If they're identical, then these two white circles will be equal in size, and where they touch is the dead center of your larger sigma 1, 3 circle. Now, the maximum shear stress will be found right at the top of any of the circles. That's the highest point. It's the maximum shear stress. The maximum normal stress is sigma 1. So it's right at the right side of the circle where it's on that sigma n line, the value sigma 1. If all three of them are perfectly equal, all you get is a dot. And it is right on this line because sigma 1, 2, and 3 are all normal stresses, so there's no shear stress happening. When sigma 2 and 3 are 0, you notice this circle is all the way over to the sigma s axis, and there are no circles inside of it, even though it's a 3D stress drawing. So A is a triaxial stress, B is a biaxial stress, whereas sigma 3 was 0. Notice it's right over here on the 0 line. C is uniaxial compression. There is not a uniaxial tension drawn here, but D is that isotropic stress, that hydrostatic stress. If we had a uniaxial tension, it would look very much like this, except it would be over here on the left side where all of the values were negative. Now another term you'll see is mean stress. And it's not when I give you homework and I'm being mean and stressing you out. Although, you know, if I give you too much, it's definitely stressful and it's definitely mean. Mean stress is the average of sigma 1, 2, and 3. And it's also the hydrostatic component of total stress. So basically it's taking, whatever's equal isotropic hydrostatic stress there is, that's one component of the total stress. Now, if you have a rock at depth, it's lithostatic instead of hydrostatic because it's pressure from rock in all directions instead of from water in all directions, but it's the same exact concept. Now, mean stress, equal stress in all directions, causes volume change. It's like if you take a balloon and you dunk it underwater, the balloon gets smaller. You pressurize gas, it changes volume very quickly and very easily. That's from mean stress or hydrostatic or lithostatic pressure. Deviatoric stress is all other stress on the object, whatever exceeds the hydrostatic stress in each of the three directions. So total stress, sigma, equals sigma mean plus sigma deviatoric. For example, you can do this in any of the three directions. So in the sigma 3 direction, the deviatoric stress equals sigma 3, the total, minus sigma mean. Or you could say sigma 3 equals sigma mean plus sigma deviatoric. Now, an important thing, the deviatoric stress is always anisotropic. This means in the rare isotropic situations, there is zero deviatoric stress. Also, very important, deviatoric stress causes shape change. So, mean stress causes volume change. Deviatoric stress causes shape change. Together, they make total stress, which can cause both shape and size change. So hopefully that wasn't too overwhelming or too dry. I want you to finish reading through chapter 3. Take a peek at chapter 4. Chapter 4 is an incredibly important chapter. It looks at deformation and strain. This tells us how we get structures. Because, okay, yeah, we've got stress, we've got gravity, we've got all these stresses happening. And I've said that they're going to cause shape change and size change, but we haven't really said how or what's going to happen. Chapter 4, we look at that deformation. We look at that strain. It's deformation that creates all the structures that we see in geology. It creates the mountains. It creates the rift valleys. It creates volcanoes even. Without deformation, we're not going to get volcanoes. We're not going to get uplift. We're not going to get subsidence. We're not going to get salt domes. We're not going to get anything. The world would be really sucky and boring without strain. And since stress leads to strain, the world will suck without stress.